Hey physics class, so I'm going to pick this up from where it was left off yesterday. Yesterday we didn't really have anything to go off of except just the beginning of this equation. Let me actually write the equation down. It was that the escape velocity is equal to the square root of 2 times Newton's gravitational constant times the mass of the Earth, or whatever you're trying to escape from, all divided by its radius. Right. So if we were to put the values for everything into that equation, we should get a value. So let's go ahead and do that. We know, obviously, 2 is 2. Now, g, if you remember, was 6.67 times 10 to the negative 11th. And mass of the Earth was big. That one was 5.972 times 10 to the 24th. It's a lot of scientific notation right there. And the the radius of the Earth was 6,372,000. Oh no. Now I'm forgetting my numbers. I'm going to go with 1. Hope I'm correct. Oh, now I got to look that up. Let's see. Nailed it. Okay. Ugh. No, this is terrible. Hey physics class, so we're going to pick this up from where we left off last time. Last time we just did the numbers on the sample of someone of my mass trying to escape the gravity of the Earth forever, finding an escape velocity, and then we just got this equation right there at the end. So filling in the values for that, we've got obviously 2 remaining itself. Newton's gravitational constant, g, is being filled in, 6.67 times 10 to the negative 11th. The mass of the Earth here is being filled in, 5.972 times 10 to the 24th. And then the radius of the Earth being 6.371 times 10 to the 6th. Well, I just wrote those down, and now I'm going to enter them in for us to see what it turns out to be. So it's going to be the square root of 2 times 6.67 times 10 to the power of negative 11 times 5.972 times 10 to the power of 24. Now we're going to have to be dividing this by, and I need parentheses, because if you're dividing by scientific notation, you always need parentheses so that you are dividing by the coefficient and the exponent. Divided by 6.371 times 10 to the power of 6. And we get 11,182. 11,182. That's not what I got yesterday. Hold on a second. 11,182. All right, hold on a second. I need to get my work from yesterday. Phew. That's what I did yesterday. So I found an energy for escape of 4.5 trillion. Did I miscount the zeros? Hold on a second. I think I miscounted the zeros. Oh no. Hold on a second. If I take this velocity and uh so let me enter this 11,182 11,000. Oh, this is terrible. 11,182 squared, and now times 37.5 times 37.5. Oh no, I miscounted the zeros. Okay, so hold on, I got 1, 2, 3, 4, 5, 6, 7, 8, 9. It wasn't 4.5 trillion. It was 4.5 billion. Oh, well. Oops. I miscounted the zero. Well, hey, of all the mistakes to make, it's not a bad mistake. Unfortunately, it's recorded. So, we're just gonna move on with that. Turns out the actual energy was 4.5 billion and not 4.5 trillion. But hey, you know, if it that the mistake was like, counting zeros, not bad. Anyway, gonna move on from this. So that is our escape velocity from Earth. Something to point out: the escape velocity does not depend on the mass of the thing escaping. After all, if the whole Galileo big rock, little rock, drop at the same rate thing teaches us anything, it's that the heavier object moving at that speed will have more energy. That's more energy for gravity to overcome. It all cancels out. So that right there, that's the escape velocity for the Earth. Okay. Well, we could actually find escape velocities for different bodies in the solar system. So this is one. I'm going to do one of them, and I'm going to leave the other to you. Two bodies in the solar system that are kind of similar to Earth a little bit, maybe. It would be the moon. So mass of the moon. I'll do the moon in blue. So we've got a mass for the moon of 7.35 times 10 to the 22nd. So the mass of the moon, 7.35 times 10 to the 22nd kilograms. We also need the radius of the moon. That would be radius of the moon. Meters. Okay, there we go. 1.7371 million meters. 1.7371 times 10 to the 6th meters. Okay, so there's the mass and the radius of the moon. Let's see, the moon is nearby. Let's do a different planet. How about let's do the escape velocity for, I'd want to do Mars, but the abbreviation for Mars is also M, and that would be confusing. So I guess let me do Jupiter. Jupiter's a big planet, right? So let's go ahead and get the mass of Jupiter. Well, that's pretty big. The mass of Jupiter is equal to a lot. 1.898 times 10 to the 27th kilograms. It is 5 orders of magnitude greater than the moon, 3 orders of magnitude greater than the Earth. It's 1,000 Earths. That's incredible. Okay, and how about the radius of Jupiter in meters? 69.911 million. Wow. Okay, so radius of Jupiter equals 69.911 million. Oh, sorry. Times 10 to the 6th meters. There we go. Okay, so between those two, that's an exercise. So I'm going to do one, and I'm going to leave one for you to do. I think I'm going to go ahead and I'll do the one with the bigger numbers. I'll do Jupiter. You can do the moon. So if we're going to do this with Jupiter, it means I will be doing, let me just scroll this a bit, the square root of 2 times 6.67 times 10 to the negative 11th times 1.898 times 10 to the 27th all over 69.911 times 10 to the 6th. And that's going to be the escape velocity of Jupiter. If you are on the outer, well, you don't really have a surface, so if you are on the outer limits of the clouds of Jupiter, how fast do you need to be going to escape it? So here's a good question. Jupiter's larger than the Earth, both in mass and in size, so is the increased mass of Jupiter enough to overcome the increased radius? We'll find out. Square root of 2 times 6.67 times 10 to the power of 11, but it's negative, times 1 point. I always feel like it's such a workout to enter numbers on a calculator, but it's really not. I'm just pushing buttons. Times 10 to the power 27 divided by parentheses 69.911 times 10 to the power 6. 60,180. Holy cow. So about 6 times faster. It's about 6 times harder to get away from Jupiter than it is from the Earth. Or I should say you have to be going 6 times faster to get away. All right, well, I'm going to leave the moon's escape velocity as an activity for you. By the way, if you have a college textbook for physics, they say that all the time. Well, they'll like demonstrate something, then they'll do some of it, and they'll leave the rest for you. It's so annoying, so I'm sorry to have to do that to you right now. Okay, so we've gotten our escape velocity for Jupiter. You're going to do the escape velocity for the moon, but now I want to make it more general because there is a way to do this backwards. As you know, with every equation, you can start with any of the unknowns and work towards any of the knowns. So rather than starting with the velocity as the unknown, let's start with a velocity as a known. Okay? So if we just reiterate this equation so that it's on this page, escape velocity is equal to the root of 2gm over r. So if we have a velocity that we know about, right? We can treat the mass and the radius as the unknowns. Now here's the thing. Because we're used to the planet Earth, it's we kind of want the mass and the radius to be connected to each other. So what I'm going to do right now is I'm going to express the radius in terms of the mass such that whatever this thing is will have the same density as the Earth. So here's the things that we are going to need for this. First of all, we know that the mass of the Earth is 5 point, oh dear, I've lost it now, 972? Yeah, 972. 5.972 times 10 to the 24th kilograms. And we also know that the radius of the Earth is 6.371 times 10 to the 6 meters. I should put the units on there, shouldn't I? Yeah, that's what a good teacher would do. So I'll put the units on there. Okay, so what's the density of the Earth? Well, in order to find the density of the Earth, we would need to know its volume. And just in case you forgot, because I did, formula for volume of a sphere. Right, 4/3 pi r cubed. How could I be so daft? All right, so that means that the volume of the Earth is going to be 4/3 pi times this radius cubed. Woo! So this is going to be big, but you know, got to work it out. I would, if we were in class, I would have one of you guys work this out, and then I would wait for the answer and then proceed. Obviously, I can't do that, so the closest I can do is just suggest that you pause it, work it out for yourself, and then watch me do it. But like, I mean, who's got time for that? So let's. Did I shrug convincingly enough for you? Let me go back to the calculator. Let's get this. So 4 times. Let's see. Do I have a? Yeah, pi divided by 3. Okay, so I got 4/3 pi times. Here come the parentheses. 6.371 times 10 to the power 6 cubed. Oh, that is a lot. That's a lot of volume. So I just had a little technical hiccup there, but we're back on track. So we've got the formula for escape velocity, and the goal is that we would have some planetary body with the same density as the Earth. Now, if we have something with the same density as the Earth, we're going to need to actually find the density of the Earth. So starting out, we've got the mass of the Earth, which is 5.972 times 10 to the 24th kilograms. Now, if we're going to find the density, we're going to need the volume, which is going to be in terms of the radius. The radius is 6.371 times 10 to the 6 meters. Okay. If you look up the formula for the volume of a sphere, you get that it is 4/3 pi times the radius cubed. But we're putting in here the radius of the Earth, so that, substituting all that, you end up with 1.083 times 10 to the 21st cubic meters. That is a lot of cubic meters. Density is mass divided by volume. So we're finally ready to find the density of the Earth. Now, you might know that the Earth is a very dense place, but we're going to actually quantify that now. 5.972 times 10 to the power 24 divided by, parentheses when you divide by scientific notation, divided by 1.083 times 10 to the power 21. Wow, there it is. 5514. The density of the Earth. 5,514 kilograms per cubic meter. 5 tons per cubic meter. So just for reference, water has a density of 1 ton per cubic meter. And so that means that the Earth is, on average, about 5.5 times as dense as water, which makes sense. I mean, most of it's rock, and rock sinks in water. You know, I'm curious. I want to know. What is the density of granite? Huh. About half that. Kilograms per meter cubed. Yeah. Interesting. Just curious about that. Granite is the most common rock that the crust is made out of. Anyway, the density of the Earth can't just be attributed to granite then. Okay, so we've got the density of the Earth here. Now we have a mass and a radius in the equation. I just noticed I have a lowercase r when the other one had an uppercase r. Don't want to be confusing anybody there. Okay, so since we have the density, what I'd like to do is re-express the radius in terms of the mass, so that the only thing that I need to worry about is the mass, and we'll let the radius... You know what? No. I think it would be easier for us to picture a different radius. Let's re-express the mass in terms of the radius. So that's going to work like this. If density is equal to mass over volume, then the mass is going to equal the density times the volume. That is, mass is equal to density times volume. Okay, so if that's the case, that means that the mass of the Earth can be represented by 5,514 times, now the volume, which is 4/3 pi radius cubed. Alright, so the beauty of all this is that all of this is just one big constant, which I can simplify in the calculator. So let's do that. 5,514 times... Hold on a second, let me clear that. 5,514 times 4 times pi divided by 3. Haha, 23,096. So I've got here that the mass of an Earth density body is equal to 23,096.9. I'm just going to round that up to 97 times the cube of the radius. Do you realize what that means? We can substitute this into there, and this is what we get. For the escape velocity of an Earth density body, V is going to equal the square root of 2 times G times 23,097 times the radius cubed over the radius. Well, this will all combine into one constant, and it will be times the radius squared. So let's simplify that. This is going to be 2 times, and now big G, 6.67 times 10 to the power negative 11 times, and now this constant, 23,097, 23,097. Hey, not bad. 0.00000. Well, that's 5 zeros. So 1, 2, 3, 4, 5, 6. That's a really tiny number, but the radius is going to be huge, of course. So we've got here, oh, by the way, r cubed and r, one cancels out. So that means that we are talking about an escape velocity, which is equal to the square root of 3.08 times 10 to the negative 6 times the radius squared. Ladies and gentlemen, for a celestial body with the same density as the Earth, the escape velocity is going to be 3.08 times 10 to the negative 6 times the square of the radius. Now, here is my question to you. How big of an Earth-sized body could you escape? Here's how you're going to solve this. I'm going to need this equation on the new sheet, but we need to understand how fast you can jump. So here is my personal test for my jumping ability right here. So as you can see, I can jump to a height of about 1 foot. That was me jumping without, like curling my legs up to try to get off the floor. It was just my legs straight. As I jump, that's just the difference in height between my feet on the ground and my feet as high as I can jump. It's about 1 foot. So if I can reach a maximum height, we'll call it H max, of 1 foot, which is 0.3048 meters. Okay, that's how high I can get. Then I can also find how fast my jump was, and that's not that hard. It's just how fast would I be going if I fell from that height. All right, so I can find a time. That's not too hard. That we require this equation, if you remember this one, right? So if I fall a height, that's my distance, equals half of, and then acceleration is 9.8, because that was acceleration when I jumped, and there's t squared. It means that the actual time it would take for me to fall, if I solve for t, is going to be the square root of 0.3048 over half of 9.8. That's how long it took for me to fall. Now, I could have just gotten the time from the video, but I'm just not that smart. So let me let me do that. The square root of 0.3048 divided by 0.5 times 9.8. Okay, a quarter of a second. It's almost exactly a quarter of a second. Okay, so how fast are you going if you fall for a quarter of a second? For that one, we're going to need this one. Acceleration is equal to VF minus VI over t. Man, or delta t. It's so nostalgic to see these equations again. All right, so I know that my acceleration was 9.8. I know that my VF is what I'm looking for. My VI was 0, so I'm just looking for V over 0.25 seconds. Okay, so I can just multiply both sides by 0.25. So, well, here, let me do that for real. 9.8 times 0.25. 2.45 meters per second. So my jump, has a velocity of 2.45 meters per second. That's how fast I can jump. Okay, now we need our equation. For a planet or asteroid or whatever it is with the same density as the Earth, the escape velocity is the square root of 3.08 times 10 to the negative 6 times the square of its radius. If I put this in there, what size planet could I possibly jump off? So here's where you come in. I do not like to make it a requirement for people to either do math on their own personal biometrics, or even necessarily take a risk on the jump and the recording and all that. So I'm not going to do the math on my own. I'm going to let you calculate that. However, that's boring and lame and kind of like so this is just my invitation to you. What I'd like you to do is to find out how fast you can jump. I mean, the velocity with which you leave the ground when you jump. The way that you can do that is by recording yourself jumping, and either get the height off the ground that you reach. And remember, this is like, if you curl your legs up, it doesn't count, right? This would just be like how much higher your center of mass is at the height of your jump than at the bottom. And you can do that by keeping your legs straight. Of course, you don't want to like land on a locked knee and break your leg. So that's one way that you can do it. Another way would be a difference between how high you can reach from the ground and how high you can reach in a jump, like that. I just demonstrated jumping while sitting. I'm so lazy. The other thing that you can do is just the time, right? So you can do this with a stopwatch or a video, but if you take a time of yourself jumping, it's the same thing. You can use that, just multiply that time by 9.8. You'll figure out how fast your jump is. Now that you've got that, you can use that velocity to figure out the size of an Earth density body that you could actually jump off of. What that basically comes down to is solving the equation 2.45 or whatever your velocity is. I'm sure most of you should be able to jump faster than me. I'm like an old man or something. And so solving 2.45 equals 3.08 times 10 to the negative 6 r squared. That would be solving that for r. That would be the radius of an Earth density body that you could escape with your jump. Just in case all this talk at the end is throwing you off, what I'm asking you to do is to solve this equation, 2.45 equals the square root of 3.08 times 10 to the negative 6 r squared. I'm asking you to solve this for r, but I'm also asking if you're willing and able to get your own number here instead of using mine, 2.45, because it's cooler when you use yours. If we were at school, we'd make a lab out of it, and like we'd pair off, and you'd do a stopwatch when you jump or something. You could all use your own numbers, but like in the circumstances where we are, I can't really control that. I'm not going to have you submit videos of you jumping. I mean, what kind of weirdness would that be? So this is just, you get out of this what you put into it. You can use my number, but it would be cool if you got your own. It'd be memorable, right? And you could calculate the size of the Earth density body that you could escape with a jump. Whew. All right. That's all for Tuesday.